Okay. Tomorrow I'm going to continue week 3. I already started it, and yeah, I finished on decision trees. Yeah, well, concept is quite hard for me, but I didn't understand some things. So maybe today it will be clear, maybe not. Yeah, how actually we use, I didn't understand did we use that, how did we use, yeah, entropy to understand not understand to predict color of the ball. So it wasn't quite understandable, but okay. So okay, let's move on. Yeah, well, okay, so let's go to the algorithms. Okay, we can make sure that the tree built-in algorithm. Okay, so here we will build like actual tree. Yeah, with some decisions. So yeah, we will have like some nodes, and yeah, so, and connection between them. Yeah, okay, so we can make sure that the tree built in the previous example is optimal. It took only 5 questions conditioned on the variable x perfect fixed a decision tree to the training set. Under other split conditions, the result tree would be deeper, take more questions to reach an answer. At the heart of the popular algorithms for decision tree construction, such as RD3 or C4.5, lies the principle of greedy maximization of information gain. At each step, the algorithm chooses the variable that gives the greatest information gain upon splitting. Okay, so last time we got definition. We defined this thing. It's called information gain. It's give us how much our entropy is going down. So if entropy is equal to the if information gain, well, okay, so what it gives actually, so we have entropy, and how do we use it? Okay, so entropy is how much uncertainty we have in our problem. That's how I understand it properly, and how chaotic is system is, and what gives us information gain. Okay, so okay, as you can see, entropy has decreased in both groups, more so in the right group. Since entropy is in fact the degree of chaos in the system, the reduction in entropy is called information gain. Formally, the information gain for split. Okay, so Ni is number of objects in which Q is equal to. Oh, okay, what is this function actually? Is it monotonic function? Is it increasing or decreasing? I'm not sure. So okay, what in the beginning we have entropy is entropy equals 1, and after splitting we got entropy is equal to 0.16. So yeah, I think should it be a decreasing function? Yeah, but if yes, so what? Why do we on every step we choose maximization of information gain? It's not so clear, I guess. Okay. Okay, then the procedure is repeated. Okay, so let's move on. I will try to understand maybe later. So then chooses the variable that gives the greatest information gain upon splitting. No, okay. Then the procedure is repeated recursively until the entropy is 0 for some small value to account for overfitting. Okay, different algorithms use different heuristics for early stopping to cut off to avoid constructing an overfitted tree. So we don't really want to to get entropy is zero in any purpose. We want to get it truly. We want to get it fairly. So we don't want just trying to create some dividing to just find entropy zero. It wasn't what we want. We want to do it like fairly and yeah, want to do it fairly. So why do we? I still don't understand why we choosing information gain to increase it. Why we choose in more and more information gain? Because in my opinion, we should increase it. I think we should decrease it, isn't it? Shouldn't we? Again, well, okay, so okay, let's move on. So okay, function build object L. Create node T. T will be our node. If the stopping criterion is true, assign a predictive model to T. Else find the best binary split left plus right left. So here we divide our 3 to the left side and to the right side. Okay, so yeah, we don't have stopping criteria, but yeah, here we build I think we call this function again. So we have here smaller tree, so we can build it like for smaller. For this one we call it again and again and again and again. So yeah, I think yeah. Okay. Yeah, I got idea, but it's still like something not so material, so I didn't really create something. Okay, so it will be on practice, I guess. Okay, so let's move on. Oh well, I think I should again open Kaggle version of this thing, because I want to, I don't know, I want to call this function and so on. And this is statistic version, so I will keep it, but just for myself. We copy and edit, usual. And oh, let's wait. Yeah, I think I can read this statistic version here. Okay, so other quality criteria for splits in classification problems. Okay, we discussed how entropy allows us to formalize partitions in tree, but this is only one heuristic. There exist others. Okay, Gini uncertainty, Gini impurity. G is equal to 1 minus some. Okay, maximizing the criterion can be interpreted as a maximization of the number of pairs of objects of the same class that are in the same subtree, not to be confused with Gini index. Okay, so what we are doing here? So we splitted our, I don't know, tree to the I don't know, subtree, our tree to subtree, for k subtree, and for each subtree we summarize these squares of probability to what is again p k. So okay, pk is the probability to find answer on, I don't know, on kth state, on ith state, ith state. Okay, it's actually not so clear how to really understand this probability, but I think we should see on examples how to do it. Okay, so misclassification error, e is equal to 1 minus max okay, yeah, so we calculate all probabilities, find the maximum value from this and choose it, and after that yeah, just use criteria for what again? Okay, not so clear as well. Okay, let's try to do further. In practice, misclassification error is almost never used, and Gini uncertainty and information gain work similarly. For binary classification, entropy and Gini uncertainty take the following form. Okay, so is the probability of object having a label plus what? Well, this is like really not so clear, not clear what they meant. Like, so if you plot these two functions against an argument p plus, we will see that entropy plot is very close to the plot of Gini uncertainty doubled. Therefore, in practice, these two criteria are almost identical. Okay, so we have our we have our interactive notebook, so we can actually build this. So okay, import our libraries because it's our first entry, and here we plot it. Okay, so what we really have here? Can I should I maybe increase this? No, it's not hard. Okay, so Gini 2 Gini. Okay. No, Miss class, 2 Miss class, Gini, 2 Gini, and entropy. Yeah, they are pretty close, like two kind of parables, two quadratic functions. Okay, so I still don't get what is p plus and p minus. Yeah, well, so binary classification, I guess it means that we choose like something we have two variants. One of them will be plus, another one will be minus, and probability to choose the first one is p plus, probability to choose another one p minus. Okay, so and okay, and okay, so okay, let's consider fitting a decision tree to some synthetic data. We will generate samples from two classes, both normal distributions, but with different means. Let's consider fitting a decision tree to some synthetic data. We will generate samples from two. Okay, so we have some data, we have yeah, got it. So we have some random data that has each of these has like some random numbers, yeah, but they are normally distributed, but has different mean values. So okay, yeah. So NP train data normalized size. Okay, so not sure how it's work. Let's try to understand it. How they really implemented it. Okay, so let's try to check every function. So I will try to understand. So it will help me to understand how it's really work. I don't think that it's so hard. Basically, it's functions that generates like random values. But yeah, not sure how to. This model implements pseudo random number generators for various distributions. Often used as a watching reduce a bit as a period of the underlying implementation involved. So yeah, let's try to check what is doing seed. Initializer is so let's try to check what's the size of it. So okay, maybe. So it has 200 values for okay, so here we got I'm not sure why we do okay, what is NP labels? Okay, so we have I don't know, we have 200 I don't know. Okay, so we have 200 random values and 200 zeros and ones. And okay, so what do we want from it? Let's plot the data. And informally, the classification problem in this case is to build some good boundaries separating the two places, the red dots from the yellow. Machine learning for this case boils down using a good separating border. A straight line will be too simple while some complex curve snaking by each red dot will be too complicated and will lead us to making mistakes on new samples. Intuitively, some smooth boundary or at least a straight line or a hyperline would work well on new data. Okay. Yeah, so what we did. So we define size of our figure. We create scatter plot, train data 1, train data 2. So we got 2 columns from this array, and the what and what is doing? What is for? So I don't know. I think yeah, I think it's define size of each dot, so they look bigger than they was before. Okay, so some kind of yeah, some kind of design, yeah, and plot from some range from 2 to 5, from -2 to 5, from -3 to how does this range work? From -3 to minus. Okay, right. Let's try to spread this. So will it work if I will do it this by 3? Okay, so yeah, I will finish this idea and go to the break. 4 and 1. What will? So it will be inversed. Okay, so actually the previous one was inverse version, and what I did is it was like straight version of the graphic. I think this one looks better. I don't know why. Okay, I don't know why this format is better than previous one, but let's try to separate these two classes by training an sklearn decision tree. We will use max depth parameters that limit the depth of the tree. Let's visualize the resulting separating boundary. Okay, so what we are doing, we import library, then let's write an auxiliary function that will return grid for further visualization. Okay, so yeah, first function is just for the grid. It's not important thing, but I think we can get rid of it. But okay, so I will watch the after break. This break. Okay, so let's go to the break. Okay, so let's move on. Okay, so the first function is just making us grid, which is not so important, but just for fancy graphic. Okay, so still tree, decision tree classifier, criterion entropy, max dev, state. So yeah, I think this function will create us decision trees that was described above with criterion entropy, not Gini index or something, and with depth of 3. So yeah, it will be just like something like that. So first question or something, second question or something. Yeah, so yeah, I think that what they meant by depth of the tree. So yeah, like this depth. Yeah, so first level, second level, third level. Yeah, so something like that, I guess. Okay, and yeah, how is it working? I think I don't know. I think it's in here, so maybe I can check it. Maybe I can check this algorithm, but I will not do it now. Maybe later. And what is random state? What is random state? Let's check. So I already met. Yes. I don't understand. I want to implement scheduling algorithm. But I don't know what is parameter random state does. Why should I use it? Yeah, that's my question. Like literally, what? I also couldn't understand what is pseudo random number. Well, I do know what is pseudo random number, because you can just create some random numbers. We need to, if we are doing some code, we need to use some kind of algorithm to create random numbers. That's why they are not purely random, they are pseudo random. Yeah, in some ways they are random, but not exactly. And so let's try to move to the answer. Okay, train test split array matrices into random train and test subsets. That means that every time you run it without specifying a random state, you will get a different result. This is expected behavior, for example. Okay, so I got it. So we actually, yeah, while we're doing tree, we split some array. So yeah, but we don't know how exactly we are doing it. So we need some certainty here how exactly we split our array or set, something like that. Decision tree. So it change. On the other hand, if you use a random state sum number, then you can guarantee that the output of run 1 will be equal to output. Your split will be always the same. It doesn't matter what the actual random state. The important thing is that every time you use 42, you will always get the same output. This is useful if you want. Yeah, I got it. So this number doesn't have like some kind of doesn't have some like ways, some we can like interpret this number, just some kind of code of this random split or something. So yeah, it's just fixed numbers that we can like documentate. And yeah, just yeah, just to repeat this result. So okay, okay. Now what we are doing? Now we feed. I don't know. And how does the tree itself look? We see that the tree cut. Okay. Did I run? No, I didn't. So okay, so in the last part we just creating this fancy graphic. So we split somehow. Yeah, just color it in red and yellow. Okay. How does fit in Voca? I still don't understand. I think we will see it. And how does the tree itself look? See that the tree cuts the space into 8 rectangles. The tree has 8 uh, leaves. Within each rectangle, the tree will make the prediction according to the majority label of the object inside it. So, how many rectangles does it have? One. So the picture looks kinda something like that. Uh, Wait a second, I have to pause it. Okay, so let's continue. Okay, so do we really have 8 rectangles here? Oh, okay, so oh, 1, 2, 3, 4, 5. Well, the bigger one 6, the the biggest one. And I don't know, I can count more than 8 actually. Well, maybe okay, one more time. Hmm. No, that's 1, 2, 5. Well, not sure how they really divide it into 8. And how does we see the tree cuts the space into 8 rectangles. I don't see 8 rectangles. Maybe in the middle 1, 2, 3, 4, 5, 6. I can see 6. Within each rectangle, the tree will make the prediction according to the majority label of the objects inside. The tree graph to PNG. Okay, so how does this things looks like? Okay, so okay, here we have, let's try. Okay, first thing that was happened, we divided all values into 2 parts. X2 is less than 1.2, 1.2 and more. So where actually is, so I think yeah, x2 is probably a horizontal line or not? No, it should be horizontal. No. Well, maybe it's actually okay. So let's try vertical line. So what it will be? So 1.2 is here. 1.2. Okay, so after that we divided on 2 parts. X1 is less than 1.2 as well. 1.5 to and second one, x1 is less than, so so 1.5, 0 point, so where do we have 0? 0 we have some, so something like that. Yeah, it looks like, yeah, I saw these lines here, so let's try to continue. that x to less 0 point. Okay, so 0 0.5, 0 minus 0. Okay, so well, I think it should be easier to just copy this. I don't know. To change page every time. Yes. Is 0 0.5. So okay, so my kitty is trying to catch my mouse. I will leave it here. So okay. Good. Get rid of my kitty again. 0 0.5. So yeah, well, maybe I will just no, I think yeah, I should keep it. So yeah, here we have length 3 of 3, so first level, second and third, like we discussed, and 0 0.5 minus 0 0.8, 1.6, 1.8. Okay, so okay, we have two lines on x, on x, axis x. So again 0 0.2 approximately and 1.5, and we have some amount of this line, some this one minus 0 0.5, 1.6, 1.8. Okay, so the not, so let's try to well, maybe I can like calculate it not just visually, but so we divide it one time, it has two parts. We divided another one, two parts into another. We got, well, I think we got six part, don't we? Maybe no. Well, maybe I should just, so, okay, one more time. 1, 2, 3, 4. And now, yeah, we have lots of things, and now we what? We took only this node that has, so yes, so not so clear as well. Okay, so yeah, maybe I will just read how can we read this such tree. In the beginning there were 20 samples instance, 100 of each. The entropy of the initial state was maximal, s is equal to 1. Then the first partition of sample into two groups was made by comparison of the value of x2 with 1.2. Find this part of the port is the picture above. With that, the entropy of both left and right groups decreased. The process continues up to depth 3. In this visualization, the more samples of the first class, the darker the Okay, so sorry again. The process continue up to the 3. In this visualization, the more samples of the first tree, the darker the orange color of the vertex, the more samples of the second class, the darker the blue. At the beginning, the number of samples from two classes is equal, so the root node of the tree is white. So, well, I got the main idea, but I still don't understand how they really how they create these rectangles. It's still not so clear for me. Okay. How decision tree works with numerical features. Suppose we have a numerical feature h that has a lot of unique values. A decision tree will look for the best according to some criterion of information gain, split by checking binary attributes such as age less than 17 and age less than 22.8 and so on. But what if the age range is large? Or what if another quantity variable salary can also be cut in many ways? There will be too many binary attributes to select from at each step during 3D construction. To resolve the problem, heuristics are usually used to limit the number of thresholds to which we compare the quantitative variable. Okay, so what we can do to resolve this problem? Okay, so we want to use some heuristics to make it work. Let's consider an example. Suppose we have the following dataset. So we have some ages and we have some on default. So some of them was refused, I guess, some of them was not. Okay. Okay, let's sort it by age in ascending order. Okay. Okay. It's already there. So HT decision tree random state 17. Add tree feed data age values reshape data value G. Okay, we see. Okay, so age less than 43.5. Age less than we see this G use the following 5 values to evaluate by age. If you look closer, these are exactly the mean values between the ages at which the target class switched from 1 to 0 or 0 to 1. To illustrate further, 43.5 is the average of it was severe old customer failed to return the loan, whereas the 49-year-old did. The 3 looks for the values at which the target class switched value value variable. Given the information, why do you think it makes no sense here to consider a age like age less than 17? So okay. I think we considered it already, so we already have it like here, age less than 18. It's included there. Okay, so okay, I will read it one more time. We see the tree used the following 5 variables. Okay, so these numbers was taken by this rule. So, for example, we have 18 and 20, so mean value of it is 19, and yeah, this is the mean value of two ages where we switch out long default from 0 to 1, from 1 to 0, it doesn't matter. Okay, so yeah, I will pause it. Oh, never mind. So I skipped it. Okay, so okay, let's try to just go to the break. Okay, let's move on. So, okay, so we classified our data set. Okay, so let's move on. Let's move on. So what we are doing next? We classified by age. So next one, what we are doing is to try to do it with salary. Okay, let's consider a more complex example by adding the salary variable in the thousands of dollars per year. Okay, so we got salary. If we sort by age, the target class will default switch from 1 to 0 or vice versa 5 times. And if we sort by salary, switch 7 times. How will the tree choose feature now? Let's see. So okay. Okay, so yeah, we I don't know, we just okay. So yeah, we have some arrays, we have some switches. Yeah, and in first one we will have 5, and in second one we will have 7. Okay. Decision 3 H. Okay, so okay, so we build tree for the salary right now. Salary less than 995 positive. So first one in the first we choose age, then salary, then age, then salary, and that's all. We see that the tree originated by both salary and age. However, that the threshold for feature comparison are 43.5 and 22.5 years of age, and 95k and 30.5k per year. Again, we see that 95 is average between 88 and 102. It's the average between two values that where we switch from 1 to 0 or vice versa. The individual with a salary of 88 proved to be bad, while the one with 102k was good. The same goes for 30.5. That is, only a few values of comparison by HSR were searched. Why did the tree choose these features? Because they gave better partitioning according to Gini and Sutton. Okay, so conclusion. The simplest heuristic for handling numerical features in decision tree is to sort its values in ascending order and check only those thresholds where the value of the target variables change. Okay, so it makes sense, I think. But I think I missed something. I didn't understand something. So okay, well, maybe I will go on. Furthermore, when there are a lot of numeric features in a data set, each with a lot of unique values, only the top n for the thresholds typed above and are selected. Only use the top n that give maximum gain. Okay, so the standard furthermore, and there are a lot of features in dataset. The process is to construct a tree of depth 1, compute the entropy question. Okay, so into illustrate. If we split by salary, the left group will have the left hand group will have an entropy of 0. All clients are bad. And the right one will have an entropy 3 bad and 5 good. You can check this with yourself. Be part of the assignment. The information gain is roughly 0.3. If you split by salary less than 95, the left subgroup will have the entropy of 0.9. And the right one will have the entropy of 0. A group contains only one object. Information gain is about 0.11. If you calculate information gain for each person in that method, we can select the threshold for comparison of each numeric feature before. An example of numeric feature discretization can be found in post sample guide to entropy based discretization. Or discretizing a continuous variable using entropy. One of the most prominent scientific paper on this subject is handling of continuous value in decision tree generation. Okay, so what is the point of this? So I think if we will choose different different thresholds, we will get different results. That's what they want to say us, maybe, in my opinion. Okay, so yeah, it's really hard to understand everything, but maybe I should focus on the example this one more time. So yeah, I think it's it feels really boring, but I guess I don't have another options to do, so let's try to do it. What are they? Okay, so I will try to calculate these numbers to understand it. So okay, what we get? So here the calculations. Well, I need just to feel these numbers. I don't feel it. I don't understand it purely. So let's try to go. So we have this thing, our data with salary and age and so on. So okay, and we have definition of entropy of Gini what? Gini uncertainty, Gini impurity, and we have information gain or entropy. So let's try to get some numbers. Second one, entropy. information gain. One of the examples of information gain. And junior in certain. Yeah, and the last one I don't need because we didn't use it, and it said that no one really used it. Why I should? Why I should? Okay, so okay, and yeah, we have all our definitions, all our things, and we can try to, I don't know, to understand it one more time. So okay, for example, if you split by salary less than the left, okay, so first thing to do is to okay, less than 42.5. So we have in left 1, 2, 3. We have two groups. Who is equal to 2. So we have here okay, we have two groups with three elements in one, and I guess 8 in the second group. So all three of them actually lone default is equal to 1. So I think it means that they were declined for getting low. So entropy, okay, so entropy here is equal to 0, I guess. So yeah, well, every possibility to get answer, did the guy like get his loan or not, is equal to 1. So no, I mean whoever we choose in this group, he will be loan declined, and we don't need him. That's why yes, that's why the probability to get a guy with loan declined is equal to 1 for every guy here. So the entropy here is equal to 0 because every logarithm is equal to 0. So yeah, and so left, all of them are bad. Yeah, like this said. Okay, so I don't know. Let's try to say the entropy is equal to 0. What is actually information gain? Well, okay, so okay, maybe I should check it. I don't know. So what actually was the number here in the original tree? Well, yeah, in our tree we split it by age. No. Yeah, we started with age. Okay, so what they get from so Genie. Okay, what was Genie? I'm not sure. Okay, so yeah, let's just I don't understand. So and the right one will have an entropy of 0.9. Okay, so what we have here? We have 8 people here, and 8 people, and one. Okay, one bet, 2, 3. 3 out of 8. So here we have 3 out of 8 bad people. No, I meant with loan declined. So what will be what they calculated? They calculated entropy. So what will be S? S will be equal to minus. Okay, so every guy here have what? I'm not sure what is PI is actually. What is probability of if state, like if you put good guy, what we will get, or like what is probability of. So well, I guess the probability to get bad guy is this one. The probability to get a good guy is this one. So do I need to what, like so for E maybe let this one like 3.3, like this sum should I need to do I need to calculate? Okay, so 1, okay, so here will be like 3 of this, and I will have like 5 of this. Is it correct? So minus 3.3 divided by 8 logarithm to 3 of 8 plus 5 divided by 5 8. So okay, and okay, so let's try to calculate it. We'll use Wolfram. Alpha site is good service. Calculate something, and so let's try to calculate it. 3 multiply by 3 divided by 8 multiply by log. Well, I'm not sure how to use here logarithm. I'm not sure how to use logarithm here with base of 2. So I need to check. Maybe not. So um 8. So it's not what I expected to get. Okay, so how did they get this number? So okay, let's try to read entropy definition one more time. Maybe it will help me. It should help me. So Shannon's entropy is for a system with n possible states as follows, where pi is the probability of finding the system in a. So we have only two possible states here. Ah, yeah, I got it. So yeah, so first state will be yeah, so I got it. Yeah, I got it. So we have two possible states. Like lone default is 1 and one lone default is 0. Two possible states, and for one we have possibility in this group this probability and this probability of the another one. And the other thing that I need to repair is here is to somehow calculate, use how to use it. Can I do it this way? Yeah, well, I think I got it. Yeah, I got the answer. Is it correct? Yeah, so yeah, I got it. So yeah, well, I finally understand how to really calculate entropy here. Okay, so yeah, and the second one we will calculate the information gain here. So information gain here is roughly 0.3. Okay, so what we will get? Yeah, here our info. Okay, so let's try to dive another one into information gain. I'm not sure how to really do it. So yeah, S0 is our first after we divided first time. So we got it like here, we got this number. So yeah, let's try to calculate information gain here. So it will be what? Oh, sorry. Yeah, okay. So it will be 0.9494954 and okay, and okay, and minus 1. Yeah, and I think we can calculate what we can calculate um mm, well, no, okay, so no, before splitting, what was information what was entropy before yeah, before splitting. Okay, so Okay, so I think I got it, but yeah, I will calculate it after break. Yeah, it actually will be really good to lower the sound here somehow, because it's actually really well. I can think I can just do. Okay, so I will be right back. Yeah, and after next Pomodoro it will be the bigger break in 50 minutes, so yeah, I will need to recharge. So okay. Okay, so let's move on. Yeah, we finished on calculation information gain. So okay, what we have. So first we need to calculate one more time S0. S0 is equal to what? We have also have two groups. Okay, we have 11 people. One more. Okay, we have 11 people, yeah, and 1, 2, 3, 4, 5, 6. 6 people with. So it will be minus 11, 6, 11. 6, 11 minus 5 logarithm 11. So try to is equal 5, 7. Yeah, so it's equal to yeah, no 0.99 close to 1, and okay, so we get 0 minus. Well, I think they have a mistake. Yeah. So yeah, well, let's try to calculate it more properly, but I guess they have mistake here. It's not 0.3. It will be 0.03. So okay, let's write this again. Yeah, here one. So, or maybe not actually. So let's try to calculate it. So we already have like two groups after we divided it. So in the first one we have entropy 0, so it will not affect anything. It will not infect in yeah, the information gain anyway, in anyways. So it will be minus what? How many? Where is it? Okay, so it will be how much? Yeah, well, I think, yeah, probably they don't have mistake here. So 11 multiplied by how much? Well, I missed this number, so it will be, yeah, this number 0.9454. So where it is again? 0.954. Yeah, and I guess it will be some close to 0.3. Let's just check it. We don't need really good accuracy here. We just want to check what is this. Yeah, well, yeah, they got good numbers, right numbers, no mistakes here. Yeah, roughly, approximately, it's really close to 0.3. Okay, okay, and well, I will not check on other numbers. I will just read. As I left some group will have the entropy and the right one will have 0. The information gain is about, if we calculate information gain for each portion in that matter, we can select the threshold occupation of each numeric feature for the construction of large tree. Okay, so what they meant by the last information gain is about 0.11. If we calculate information gain for each portion in this matter, we can select occupation of each. So okay, so before we start like building the large tree, we can just construct like a tree with only like one depth or two depth, I guess, and select one that gives us more information gain or gives us less entropy, and it's probably in this example it has like this, probably because it gives us more information gain. Okay, so well, I think I got why information gain we should maximize information gain, because the more information gain is, the like this. So okay, so one more time. Information gain. Yes, so for why again? Oh no. Information gain before was high. So information gain will be high. So we have S0, we have initial entropy. Okay, so this is like constant. So if information gain is high, so AG is equal to S0 minus something. So that is this thing, let's call it A, I don't know. This thing is depends of our subtraction, of our dividing, of our splitting groups, of our splits, and I don't know. Of our, it depends on features, numerical features. So A is equal to S0 minus IG. So the bigger IG is, the less this thing. So okay, so if IG is increasing, I thought that we want to subtract as much as possible from initial information gain. So if initial gain is increasing, this thing that we devise is decreasing. So why do we need to like to save entropy? I'm not sure, or what is my mistake. Okay, so maybe check Google and Wikipedia probably, so it will give me. Okay, so information theory, machine learning is a synonym for Kullback-Leibler divergence. The amount of information gained from about render variable or signal from observing another. Well, from like intuitively, it's good to have like more information gain. Like we are getting something like something good from it, like something new that will help us. But from I don't think that it help us with some kind of I don't think that it help us. I don't understand formula. Why do we need to maximize it? Formula is not so clear. The term is sometimes used much, which is additional expected value. Gain of so some kind of distributions. I'm not sure what it is. D is what? D is no, I don't know. Dispersion maybe. Expected value. This concept can be used most. Okay. Yeah. Okay, so these things I understand. These things I understood. It took some time, but in general it's fine. Yeah, like if you like take like one sample, you will like break everything into groups, and it's not so hard to calculate probabilities. So here we calculate entropy. Okay. I know how to calculate it, so it's no problem for me. How can we quantify the quality of split? Let's consider the split again. Before the split we have, okay, after the split we have two branches. Left branch has, so yeah, it's true. Second one, now that we have the entropies of both branches, and determine the quality of the split by weighting the entropy of each branch by how many elements it has. Since leverage has 6, so well, well, I wasn't okay. So how much entropy we removed. Ah, no, I was right. Ah, So, yeah, one more time. So what is the thing that we divide? This thing is equal, actually is equal to, is equal to the entropy of the split. And yeah, and we removed it. So yeah, so the less we remove, the more. Well, yeah. So yes, yeah, I think it's fine. So the more gain is, the less this value. Because what is this value? This value is what we actually have. What entropy is left in our task. So yeah, information gain is equal, is increasing. This thing, I mean, as split is decreasing. So yeah, it's fine. Yeah, it should be decreasing. Yeah, I got it. So yeah, well, it took some time, but in general, I think it's good. It's good thing to stop here. Well, because actually I wasn't like really didn't understand what happened before. So yeah, well, I got the main idea, but yeah, well, I actually really glad that I'm stopped here. Okay, so now we can move on actually. Crucial tree parameters. Technically, you can build a decision tree until each leaf has exactly one instance, but this is not common in practice when building a single tree because it will be overfitted or too tuned to the training set and will not predict labels for new data. Well, at the bottom of the tree, at some great depth, there will be partitions on less important features. Whether a client came from Leeds or New York, we can exaggerate this story further and find that all 4 clients who came to the bank for a loan in green users didn't return the loan. Even if that were true in training, we don't want our classification model to generate such specific rules. Yeah, well, so the more we build tree, the more we will like get some really not important rules or really not important like dependence. So we don't want to get it. Yeah, there are 2 exceptions where the trees are built to the maximum depth. Random forest. Group of trees averages the responses from individual trees that are built to the maximum depth. We'll talk later on why you should do this. Okay, so what again? Random tree. So where we want to pick maximum depth. What is maximum depth again? It's tree where after all splits we will have in every like partitions we have only one element. And okay, so random forest, a group of trees averages the responses from individual trees that are built to the maximum. Okay, so average the response. So yeah, we build like everything, every trees probably, and take like average response. I'm not sure what it is actually and how it's calculated, but yeah, I think I can like imagine like somehow what it is like. We have lots of trees. I don't know, like one tree we divide somehow. Another one, another one, another one. Yeah, and we somehow like built like average of it, like I don't know. For example, if we took like one element, it has like here we like classify it, here we not classify it, and here we classify it. In average, we should classify it and like don't watch on this one. But it's just my opinion. Maybe I'm not sure what it is. Okay, and next one, running trees. In this approach, the tree is first constructed to the maximum depth. Okay, well, so bottom up, some nodes of the tree are removed by the code and without the partition. Okay, so again, we built somehow tree with maximum depth. Okay, good to see. And what next? After that, then from the bottom up, some nodes of the tree are removed by comparing the quality of the tree with and without this partition. How to compare it? Okay, so we somehow can remove some nodes. Okay, it's fine. So, and what else? And after that, we can compare like initial tree with the tree with removed nodes, with some of removed nodes, and maybe yeah, it will be better. How to compare it? This is cross validation. What's cross validation? It will be below. Okay, never mind. Because the picture below is example of dividing borders built in or in an overfitted tree. Okay, let it be. So the most common ways to deal with overfitting in decision trees are as follows. Artificial information on okay, the most common ways to deal with decision trees are as follows. Artificial limitation of the depth or a minimum number of samples in the leaves. Visual tree just stops in some point. Okay, so one way is just to create some limits. Some of them are artificial, some of them like from common sense maybe. Okay, so we should we can create some borders. Okay, yeah, it makes sense. And the first one is like to prominent, like it was discussed below above. Okay. So the parameters of the SQL class are max depth. Okay, it's understandable. Max features. The maximum feature with which to search for the best partition. This is necessary with a large number of features because it would be expensive. Search for function for all features. Okay, and mean some number of leaf. Not create a list where any leaf would have only a few members. Not need to be set depending on the data, and it's usually done by means of cross relations below. Okay, so the parameters of the tree. Yeah, well, parameters are quite clear, so I think I saw it already. Yeah, and the parameters of the tree need to be set depending on data, and it's usually done by means of cross validation. More on this below. So Yeah, so again, it will be described below how do we really choose these parameters. So one thing, I still think that we can use some common sense, maybe like from our experience, but maybe the better way is use this method, cross validation. I've heard about it somewhere, but I'm not sure what exactly it is. So it should be described. Is it described about below? Nearest member, choosing model and cross validation. Yeah, here is cross validation. Well, yeah, it's a long lesson, but yeah, like it was said, it's important one. So yeah, it has like lots of it has like lots of like core definitions, and good to important to set it at least there. Okay, so yeah, yeah, what I want to say, I passed 4 Pomodoros. I work for like 2 hours with some breaks. So right now it will be long break, and after that I will do 2 more Pomodoros. Yeah, and I'm not sure that I will be able to end this topic, this theory, but I don't know. I will try. I will just try. Anyway, it's just important to, I don't know, to get through this, like really hard, like to understand most of it. It's not so hard, but still fine. Yeah, well, and maybe I will last my Pomodoro I will spend on yeah, I will not, yeah, I will definitely not be able to finish it. I will last Pomodoro will be on some organizations. I will try to choose to find maybe some good courses to find. I want to find some courses that has good like explanation for mathematical statistics, because I have some gaps in this topic, and it will be great to cover it. So yeah, and it's actually more easier to like spend some time on it. It will be some kind of like relax, some kind of rest for me, just to go through surfing the internet and just find some courses. It's much easier. It will be much easier for me. So be right back. Go to the break. Okay, sorry. Well, I didn't feel well. Needed some extension for my break. Okay, so like I said, one more Pomodoro for the for the continuous of this topic of this week, and after that I will go for surfing internet just to check something, just to find some courses that I maybe want to listen. Okay, so when predicting, what I finished already is yeah, we discussed before some parameters, some trees parameters. Yeah, and how can we like choose them? How should we optimize them? Yeah, and yeah, so okay, so let's move on. Decision tree in a regression problem. When predicting a numerical variable, the idea of a tree construction remains the same, but the quality criteria changes. Variance. D. Okay, so 1 divided by L. Okay, so it looks like it looks like how it says mean and dispersion. It looks like dispersion. Okay, where L is the number of samples in a leaf, I is the value of the target variable. Simply put, by minimizing the variable we took for features. Well, simply put, by minimizing the variance we took for features that divide the training set values of the feature in each leaf roughly equal. Yes, so one more time. So all we want to do is put okay, so in every part, in every split of training session we put values that are very close to each other. So this thing will be, we want to minimize it. Okay, so let's generate some data distributed by the function. Okay, with some noise. Then we will train a tree with this data and predictions that the tree makes. Okay, so some variables, function. Okay, this function will get us some amount of numbers that are distributed in this way with this function. So I will what I want is just to check what does this function do. Rail oh, in Python np-rail return a continuous flattened array. One day input is returned, copy is made only. Okay, so yeah, it will give me array of yes, so I'm not so sure what so, Yeah, well, maybe it will give us array. Well, okay, so instead of x, we will like use array of x. X, I don't know. Okay, and what next? Dev generate and samples, noise, x, be random. Oh, so here we generated be random. So what we're doing here, we took some sample, add some noise from I think it's from range. It will be in range from -5 to 5. Yeah, it will be. So this thing is probably gives us random variables in a range of from 0 to 1. But if we multiply it by 10, we will get sample from 0 to 10, and then subtracting 5, we'll get from -5 to 5. Okay, we will sort it. After that we sort it, like add it to array, continuous. Then we got this axis and put it into this distribution. And after that we will add some random noise with mean. So and I think here we got like vector. Yeah, maybe. Okay, so x train, y train, generate sample. Yes. So and here we got an sample train. So we got two sets of data. One is train data, second is test data. So I think train data must be higher, must be more than should has more elements than test data. Okay, import decision tree, rect3 decision tree, max def it. So we are training on training data. And fixing on test data, and after that we just plot a graphic. Yeah, this thing is just fancy thing. So okay, we see that the decision tree approximates the data with a piecewise constant function. So okay, we have some sample. Here we have these dots are just for our data. This smooth function is our distribution function, and this constant things is our approximation. Okay. Okay, so what will happen if I just if I just uh, switch here the size of samples. Train. So we got more dots, and I'm not sure is it better or worse. Okay, so yeah, well, it looks like it's better, but who knows? So let's just send. Okay, so let it be that is so. Okay, so next topic, the nearest neighbors method. Okay, nearest neighbors. Okay, is another very popular classification method that is also sometimes used in regression problems. Okay. This, like decision trees, is one of the most comprehensible approach to classification. The underlying intuition is that you look like your neighbor. More formally, the method follows the compactness hypothesis. If the distance between the examples is measured well enough, then similar examples are much more likely to belong to the same class. So what is wait, what I want to do? I forgot. So okay, according to the nearest neighbors method, the green ball would be classified as blue rather than red. According to the nearest method, the green ball would be classified as blue rather than red. Okay, so idea is quite fine. It's quite understandable. For another example, if you do not know how to tag a Bluetooth headset on an online listing, you can find 5 similar headsets, and if 4 of them are tagged as accessories and only one as technology, then you will also label it under as accessories. To clarify each sample from the test set, one needs to perform the following operation in order. Okay, one more time. To classify each sample from the test set, one needs to perform the following operations in order. Calculate the distance to each of the samples in the training set. Which, okay, so, well, what is the distance? I think maybe it could be like difference. Probably if we have dots on plane, it will be distance like between two dots, which is also like understandable things. Select case samples from the training set with the minimal distance to them. Select case samples from the training. Okay, so the class of the test samples will be the most frequent class among these k nearest snaps. Okay, one more time. Okay, we calculated distance to each of the samples in the training. Okay, select k samples from the training set with the minimum distance to them. Between them or what? I think so. The class of the test sample will be the most frequent class among those k nearest name. Okay, the method adapts quite easily for the regression problem. On step 3, it returns not the class but the number, a mean or median, of the target variable among neighbors. The method adapts quite easily for the regression problem. On step 3, it returns not the class but the number. A notable feature of this approach is its laziness. Calculations are only done during the prediction phase, when a test sample needs to be classified. No model is constructed from training examples beforehand. In contrast, recall that for decision trees, in the first half of this article, the tree is constructed based on the training set, and the classification of test cases occurs relatively quickly by traversing through the tree. Nearest neighbor is a well-studied approach. There exist many important theorems claiming that on endless datasets, it's the optimal method of classification. The authors of the classic book The Elements of Statistical Learning considered K and N to be a theoretically ideal algorithm. Usage is only limited by computation power and the curse of dimension. Okay, so what is KNN again? Did I K nearest neighbor? Okay, KNN. Okay. Okay. In real approach, KNN can serve as a good starting point, baseline in some cases. In Kaggle competition, KNN is often used for the construction of meta measures. KNN predictions as input or for stacking blending. The nearest neighbor method extends other task recommendation system. The initial decision would be a recommendation of a product that is popular among the closest neighbor of the person for whom we want to make a recommendation. In practice, on large datasets, approximate methods of search are often used for nearest neighbors. This is a number of open source libraries that implements such algorithms. Check out Spotify library online. Okay, the quality of classification regression with KNN depends on several parameters. The number of neighbors, the distance measure between samples, common ones, includes Hamming, Euclidean, Poisson and Minkowski distance. Note that most of these metrics require data to be scaled. Simply speaking, we don't want the salary feature, which is on the order of thousands, to affect distance more than age, which is generally less than 100. Yeah, it's quite understandable. So yeah, basically this means that yeah, if you took like different type of data, we could get like really big difference in data in distances. So yeah, it would be like not so good. Weights on neighbors. Each neighbor may contribute different weights. For example, the further the sample, the lower the weight. Okay, so I think, well, one more time, from where we compute distance. The distance of each of the sample in the training set. Okay, well, not so sure. Okay, so we will try to track this question. So how exactly do we calculate the distance between what? Between everything to everyone and everyone? So the main parameters of the class. Main parameters of the class are weights, uniform, all weights are equal. Distance, the weight is inversely proportional to the distance from the test. Well, I think I got it. So we take test sample and everything from we just try to calculate like distance between dots and some kind of set, or I don't know, some kind of thing like on the plane, for example. Yeah, for example, we have test set, like some kind of dots. This is some kind of, yeah, and we have like this sample, and like the closest dot of this shape is our distance. Well, yeah, and we have like these, and I think if we have like some dot in this shape, so choose distance to the closest dot, I don't know, something like that. Yeah, well, I think it's probably what I will looking for. Okay, algorithms are optional. Okay, so well, or any other user-defined function. Okay, so I can calculate weights in every way that possible. If we can like define function for it. So okay, algorithm optional brute, ball tree, KD tree, or outer. In the first case, the nearest neighbors for each test case are computed by grid search over the training set. In the second and third case, the distance between the examples are stored in a tree. Accelerate finding nearest neighbor. If you set parameter out to auto, the right way to find the neighbors will be automatically chosen based on the training set. Okay. Leaf size optional. Threshold for switching to grid search if the algorithm for finding neighbors is ball tree or KD tree. So if we choose some kind of tree here, so we can like what is the threshold for switching to grid search? Okay, metric. Okay, so well, I don't remember. I only remember Euclidean metric. What is it? It's like if you have two dots with some coordinates, so distance between them could be calculated by equal to x2 minus x1 here and square from it plus the same for the second coordinate. So this is Euclidean metric, and that's how like we calculate distance like on the plane, or I don't know, between some like close distance. Yeah, but yeah, in general, that's not the best approach, because we live not on plane, we live on a sphere. So yeah, we should. Yeah, well, yeah, we should use another matrix than just this one. So okay, well, okay, like I think, yeah, I will go to the break one more time, and after that, yeah, I will stop here on choosing model parameters and cross validation. Yeah, because it's, I think it's, yeah, another paragraph, another topic. Yeah, and actually I think I will or maybe not. Okay, anyway, at least I think I can try to cover it, because today I covered half of this lesson, and maybe if I spend one more pomodoro on this, maybe yeah, I will go any further. So probably tomorrow I will cover it. Yeah, so yeah. Okay, so I think I like this theory. It's kind of like, I don't understand not most, I don't understand some details, and especially some codes in codes, but idea and some math in here, some seems good, and it has based on all has theory, and yeah, well, yeah, so there is a theory behind like these explanations, these ideas. So it's one of things that it could be good to check like maybe later, or maybe off stream, I don't know, maybe on stream. Okay, so yeah, I will go on the last break, and we'll Okay, so last pomodoro, last part of the stream. I will go, like I said, I will go just through the internet. I'm surfing. I want to find some courses that will help me to better understanding of mathematical statistics and maybe Python. I don't know. Let's just, I don't know what I wanted to search. Well, I already forgot. Just okay. Well, first what I wanted to check is, yeah, Khan Academy. Well, it looks interesting. Looked interesting when I heard about it first time. So let's just try to watch what it is. Well, maybe can I just skip this part of registration? Yeah, can I just look through this? Okay, so calculus, statistic, pre-calculus, geometry, differential questions. Well, statistics. Okay, let's go through this. Yeah, I think I should. Okay, so let it be. Okay, so IP statistics. Meet one IP content creators. Former high school teacher for 10 years. Alama. Analyzing categorical data. Tables. Displaying right data. Histograms. Okay, so this is like explanation for data, some different types of data. Okay, so summarizing quantitative data more on mean and median in modeling percentiles, density curves, normal distribution, and bivariate data making table, bar plot, correlation, least, and variable. What is? Yes, so yeah, well, things that I want to cover, I think like this one, random variables, sample distribution, yeah, confidence intervals, yeah, hypothesis testing, yeah, it's also really hard for me. Yeah, and what's more, the sensitivities between two proportions. Okay. Well, it looks interesting. Maybe, yeah. Well, yeah, it looks interesting. Yeah. So, yeah, maybe I will finish my searching in here. So, yeah, what I want to do, like, well, can I Okay, well, can I edit somehow? Okay, so let's. Okay, so can I edit somehow? For this course, as knowledge of the skill, have a test coming up. First change can help you understand what you need to review. Wow. Okay, so well, maybe like next time. Well, but looks interesting. I think, yeah, I will not be able to answer lots of questions, but statistics is very bad. Is my bad, my like weak part. Okay, so calculus, maybe multivariate calculus would be nice. Math, reading, no, it's not for me. Computing, computer science. Well, okay, so maybe Python would be nice to revise. How of code. Try an hour. How many ways? How of the problem? How of the data? Your own custom store. Well, I had one internship. I had to do a music store. Side of music store. Well, not so great, but okay. So yeah, I don't know. Just maybe it's good it's good to check it after all. Okay, so finance. Yeah, it would be great like one day to check some finance costs. Also interesting. Okay, so what's next? Do they have Python? Programming. Intro JavaScript, I guess. So yeah, this is like a hour of coding probably. What gave us. So do they have Python? Python. Not sure if they have it, but okay. Okay, so one course is good. Well, should I check one more? Maybe Coursera? I will start with statistics. It's just basic statistics, Python statistics, or So let's check some of them. Well, not sure if I need basic statistics. Let's just create independent visual. Well, I think it's good, like maybe it's good addition to the main course. Yeah, well, but maybe another time. So, okay, where I am. We live in uncertain and complex world. Well, it feels like it's just, I don't know, just basic tutorial. Yeah, well, what I need is like pure math here. And I don't. Statistics.
Hi.
Yes, so it doesn't feel like, well, it has lots of course, but it's hard for understand. It's good. Oh, it's me. YouTube has lots of courses. Well, it has lots of lectures, but they're not just courses. Yeah, well, I saw some of this, some of those videos. Yeah, for data structure. So maybe it's worth enough to watch it. I don't know. Well, in 8 hours. Maybe I can go on long stream. 8 hours stream. Yeah, maybe it's a good idea. I don't know. Well, if I will watch it, I will watch it for like more than 8 hours. So, yeah. So I'll try to understand everything, but maybe it's not a good idea. Well, well, first what I can do is I think what I can do is I can watch on speed too. So I don't know. I can try to. Can I watch video while I'm streaming? I think no. Okay, so 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 well, lots of videos. Yeah. Well, the cons of videos that it doesn't have like lots of practice, and practice is really important here. So pure theory is not good. Okay, so maybe I can what I can do. I can check on Reddit something, some kind of sources maybe. But Han courses looks promising at least. So it has like some structure. Well, I'm pretty sure that it has what else? I'm pretty sure that it has like lots of tasks, and I can check myself. But yeah. But yeah, I need to test it at least. So I watched some of the courses from this site, and they were fine in my opinion. Okay, so what I learned. Okay, does it have your statistic? Um, uh, few more programming languages. Okay, so looks interesting. Okay. Yes, so let's try to check. This guy doesn't know how to learn by yourself. So let's check. Statistic versus at The gradient, check one of these. Well, it's yeah, it's more about practice, which is good, but yeah, I don't know. It feels like I don't have like some kind of structure in my head. Yeah, I think it's from this side as well. Maybe not. Yeah, it's just same thing. Yes. Yeah, well, I don't know. So well, okay, I think yeah, well, I found one course I liked the most. I'm not sure. Yeah, I think I can. At least I can start with it. So okay, let's just. I think yeah, I will call out a little bit earlier, but I don't want to start to continue this one in 3 minutes, and I'm not sure that yeah, I don't really want to like research in other courses. Well, I mean, I think I found the most like interesting for me. Yeah, well, maybe I will, if I will not enjoy this, I will try to something more. Well, because it was hard for me to find. So, okay, thanks for watching. I will be back tomorrow.